Hi everybody, welcome back to another video. In today's video, we are going to talk about the membrane potential. Now, we're going to talk about what the membrane potential is, how do we actually achieve it, and what is the membrane potential of a neuron? Because, well, that's what we're going to be discussing in these few series of videos. Okay, so the membrane potential. Guys, the membrane potential is the separation of charges across a membrane. Okay? Separation of charges across a membrane. To expand on that, we can actually say that it is really the difference in concentration, okay? The difference in concentration of cations, which are positively charged, and anions, which are negatively charged, in the intracellular fluid and extracellular fluid. Okay? So the membrane potential is not only the separation of charges across a membrane, but really we can define it as it's a difference in the concentration of positive and negative charges in the ICF and the ECF. Okay? Again, ICF being intracellular, ECF being extracellular fluid. Now, remember, this is really important. All cells have the membrane potential. All cells have a membrane potential, and we'll talk about why, okay? And how is it that they all have it. But only some cells can change it. Okay? And that's what the next two videos will actually be. They'll be about graded potentials and action potentials, which are really just us changing our membrane potential. Now, the cells that can change it are things like neurons and muscles. And you'll see that, we have three different types of muscles, right? The cardiac, the smooth, and the skeletal muscle. And all three of them have the ability to change their membrane potential. And of course, neurons can do it as well, which is what we're going to talk about. Okay, what is the membrane potential actually influenced by? Well, remember, I said that it is really defined as the difference in concentration of cations and anions in the intracellular fluid and the extracellular fluid. If you remember, we can have a lot of different cations and anions. So, for example, sodium is a cation, potassium is a cation, chloride is a anion because it has a negative charge, right? These are the charges in question. Okay? So that's that. All right. Now, if we go back to my plasma membrane video, you'll remember that I mentioned that any molecule, specifically ions, that have these kind of charges, not only do they exhibit a kind of chemical gradient or concentration gradient, they exhibit an electrical gradient as well. So the membrane potential is really also influenced by the ion's electrochemical gradient, okay? And it could be any one of those ions we talked about. We'll come to see that it's more so always going to be the sodium and the potassium ions. And also membrane permeability, okay? So, and membrane permeability. Now, remember, we will talk about how each of these kind of translate into our big diagram over here, okay? But for now, I think it's good to understand that a membrane potential, if I want to really define it bare bones simply, is the separation of charge across a membrane, okay? A charge would be like positive charge, positive charge, okay, sure. And the difference in concentration of cations and anions between the ICF and the ECF is the better definition. We know that all cells have this membrane potential, but only some cells can change it, such as neurons and muscles. We know that the membrane potential is influenced by that ion's electrical and chemical gradient, and whether the membrane is permeable to that ion or not. Because remember, how could we have a separation of charge across the membrane if that charge cannot pass through the membrane? So membrane permeability must play a role as well, right? And we'll come to see what I mean here by that, all right? But first, let me make sure you guys all understand what is actually a potential, okay? So let's say I have a one positive charge, one negative, one positive, one negative, and another positive, negative, positive, negative. Does a membrane potential exist here? The answer would be no, because I have two positive charges, I have two negative charges here, and I got two positive and two negative here, okay? There is no membrane potential. The charges, sure, there might be on either side of the membrane, but they're not separated, okay? They're not separated. These areas are currently electrically neutral, meaning there is no net difference between them, right? Because we said a membrane potential is a difference in charges. There is no difference in charges here. We got two positive, two negative, two positive, two negative. There is no difference, right? This black guy was being the membrane here, okay? All right, let's take another scenario. Let's look at this example. In this example, right, let's say this is the extracellular fluid, so outside of the cell. This side is the intracellular fluid, and this guy is the membrane that's separating charges, okay? Let's say now we have 5 positive charges outside, so 1, 2, 3, 4, 5. And I'll have 2 negative charges outside, 1 and 2. Inside, I only have 1 positive charge, but I have 2 negative charges. Question, is there a membrane potential here? Yes or no? If you're saying yes, pat yourself on the back, okay? Because there absolutely is a membrane potential here, okay? There is a separation of charge. There are 5 positive charges here where there is only 1. Now, let me ask you this. Which side is more negative, the outside or the inside? Again, if you said the inside is more negative, then again, pat yourself on the back. Now, you might be questioning me here and saying, hey, wait a minute. The outside has 2 negative charges and the inside has 2 negative charges. So how come you can say that the inside is more negative? Well, it's not really always about which side has the more negative charges. It can also be about which side has the least positive charges. Because an absence of positive charges makes one area more negative compared to the other area. For example, over here, here's the membrane separating the inside and the outside. Outside, I have 5 plus charges, 2 negative charges. Inside, I have 2 negative charges, but only 1 positive charge. That means that the inside is more negative compared to the outside because I don't have as many positive charges, okay? Now, I can change this scenario and I could say that I have 5 positive charges, 1, 2, 3, 4, 5, and I could say that I have 3 negative charges here. In this scenario, a membrane potential still exists because there is a separation of charge, and the inside is negative as well, still, but not due to having less positive charges. Instead, it's due to having more negative charges. Okay? Great. So, imagine this. Let's take the scenario again. I have 5 positive and 5 positive. Okay? So 5 positive charges outside, 5 inside. If a positive charge from this side happens to leave the cell, okay, what happens? The outside gains a positive charge and becomes 6 positive, and this side loses a positive charge, so it becomes 4 positives. But understand that the positive charge that just left the cell made the inside of the cell negative relative to the outside. Okay? Because now, look, now we got 4 positives versus 6 positives. Okay? So the inside is more negative compared to the outside. Doesn't mean that it has this negative symbol, but it's more negative relative to the outside. Okay? Good. That's really important to understand. Now, whenever we're talking about charges, right, such as these positives or negatives, right, I'm sure you guys have heard of a unit of measurement called a voltage, okay? Anytime, you're plugging in your electrical device, right, your charger or whatever on it has a specific voltage that needs to be met, right? We've all seen that. Well, because a cell is so small, and these charges are so minuscule coming from our ions, right? Like potassium, like sodium. These charges are very minuscule and tiny. We don't use a unit called voltage. Instead, we call it millivolts, okay? Or millivoltages, okay? Which is just 1/1000th of a voltage, okay? So if you want to go from a millivolt to a volt, you just got to divide by 1,000. Okay, just a little bit of clarification there. So all of these positive or negative charges, they would be measured in voltages, okay? Specifically millivoltages. Great. So what is the membrane potential of a cell, specifically a neuron? Well, the resting potential of a cell, and in fact, most cells, would be somewhere around a -70. Okay, so resting membrane potential, RMP, and I'm going to put resting, and I'll tell you why I'm doing that in a second, is -70 millivolts. Okay, this is indicating to me that the inside of the cell is very negative. Okay, great. And the outside of the cell, we don't usually give it a voltage. We said that it's kind of electrically neutral. We say it's maybe 0 millivolts. Doesn't really matter. Okay? The other thing I must really emphasize is when we keep saying there's a difference in concentration of cations and anions in the ICF and ECF, we're really talking about a very specific location. Imagine this whole thing is a cell. The black is the membrane, right? Anything outside is the extracellular fluid, or, the interstitial fluid, right? If I have a cell, such as this guy over here, right? The entirety of the cell will have charges all around it, right? Because, these sodiums, these potassiums, magnesium, chloride, whatever, all of these kind of charges, they're all kind of distributed across this actual cell cytosol. Same thing for the outside of the cell. So, am I really saying that there has to be a difference in concentration of cations and anions from the entirety of this guy and the entirety of that guy? No. Where does the difference actually take place? The difference is right along the membrane. Okay? Okay? That difference in charge that we keep saying is our membrane potential exists right along the membrane. The rest of the extracellular fluid and the intracellular fluid are in complete electrical neutrality with one another. It's just this portion of the membrane that is kind of separated by different charges, and it's that portion of the membrane all along, that has that membrane potential. Okay, alrighty. So if the resting membrane potential is indeed -70, how do we get there? Or how did we get there? Because we must have started from 0 millivolts, right? We must have started from no charge, and then we must have worked our way out, down actually, to -70. So how did we do that? How did we get there? Well, I'll tell you how we get there. If you remember, in our discussion of the plasma membrane in a plasma membrane video, we said that there's a very specialized transporter that exists on the surface of every single cell you have. This guy is called the sodium and potassium ATPase. Okay? We said that this guy is responsible for taking, and you know what? I'm going to do it in this different color, just so it's all color-coded with one another. We said that this guy, the sodium potassium ATPase, is responsible for taking 3 sodium ions from inside of the cell and pushing them out, okay? And taking 2 potassium ions from the outside of the cell and bringing them in, okay? Alrighty, so 3 sodium out, 2 potassium in. We said that this guy this sodium potassium ATPase, he is the one that is establishing the concentration gradients that we know so much and we love. What are those concentration gradients? The concentration gradients are that sodium, because it was taken outside from the cell and pushed outside, right? It would be higher outside. Right? That's why I depicted it so big, because it's higher outside, and it would be much, much lower inside. Okay, so higher, lower. Great. What about potassium? Well, I took potassium from the outside and I pushed it inside, which means, or must mean, that potassium must be really large inside, and it must be very, very, very small concentration outside. And I think that should make sense to everybody. Okay. But that's not the only thing this guy is responsible for. Okay? He's responsible for generating the concentration gradients, absolutely, for these ions. But he's also doing something else. Notice, 3 positives leave, 2 positives come in. Wait a minute. That's a net negative. Okay? That's a net negative charge that this guy's generating, meaning that I'm losing more positive charges than I'm gaining back, right? Because I get rid of 3 and only 2 come back. So every single time this guy is working, he's making the cell just a little bit negative. Just a little bit negative. Well, what did we say our resting membrane potential is? We said it's negative 70. So this guy right here, he's making the cell negative. By how much, you might ask? Well, and you know what? I won't even write it because it's not worth it. But the sodium potassium ATPase generates a membrane potential of around 1 to 3 millivolts, okay? So it's making the cell negative by maybe 1 to 3 millivolts, all right? Now, this dude is, percentage-wise, responsible for 20% of the resting membrane potential. Resting membrane potential. He contributes about 20% to the resting membrane potential by making the cell just a bit negative. But remember, one of its important functions is it establishes the concentration gradient. That's really key. Okay? Now we're going to talk about that concentration gradient. We know from, again, Fick's laws of diffusion that any ion has a chemical or concentration gradient, and it also has an electrical gradient, okay? Recall that things like to go from positives to negatives, right? Like, if I am a positive charge, I would be attracted to anywhere that is negative, okay? And vice versa, okay? And if we have a negative, they tend to repel each other. And same thing with a positive and a positive, okay? Why am I telling you this? All right. So here's potassium, right? If the inside of the cell is truly negative 70 millivolts, right? Remember that, first of all. Inside of the cell is negative 70 millivolts. And the concentration of potassium is really high in the cell and it's really low outside. Where would potassium like to go? Well, potassium will go down its concentration gradient outside of the cell, right? It'll go out through these channels here. Okay, we'll talk about what these channels are called. But for now, just understand that it'll go out from these channels. Now, remember this that I mentioned. Anytime a positive charge is moving outside of the cell, what's going to happen? That positive charge is leaving the cell a bit more negative than it was, because positive leaks out, right? And if the positive charges that were inside move outside, those guys will be now outside, and the inside will remain a bit more negative than it was. Okay? So potassium moving out throughout these channels, right, is contributing to that negative resting membrane potential. But that's not all. Potassium is not the only ion involved. Sodium is involved. Remember, we established a concentration gradient for sodium. Sodium is high outside but low inside. It likes to go down its concentration gradient and move inside of the cell, making it a little positive. Okay? So again, here's sodium moving in, making it a little positive, whereas this guy will move out and make the cell negative. So you might be thinking, hey, wait a minute. If positive charges are going out, right, making the cell negative, but positive charges are coming in, making the cell a little positive. How come we're at negative 70? How come the end result is a negative number and not a positive number? Well, that has to do with something called the equilibrium potential of each ion. Okay? So first things first, let's discuss electrical gradients. Potassium, we know its concentration gradient is telling it to go outside, and we know sodium's concentration gradient is telling it to go inside. But you know it's an ion, it has a charge, so we have to talk about its electrical gradient. Well, if the inside of the cell is truly negative 70 millivolts, right, which means it's more negative than outside, then positive likes to go towards a negative area. So we know that sodium moves with its electrical and chemical gradient, Cg. What about potassium? Well, potassium at resting membrane potential, right, which is negative 70, is moving with its concentration gradient, right, moves with concentration or chemical gradient, right, but it's actually moving against its electrical gradient. Why? Well, because it's a positive charge and it's moving from an already negative area to a less negative area. Why would it do that? Well, it's doing that because its concentration gradient is much more stronger than its electrical gradient. Okay? So it's dominating at the moment. The concentration gradient is much more dominant in this moment than the electrical gradient, so potassium's getting pushed out. Okay, so against the electrical gradient. Okay, what does this have to do with the fact that the membrane comes down to being negative 70? Well, let's take a look at some numbers here. Okay, potassium in the extracellular fluid, all right, has a concentration of 5 millimoles per liter. And in the ICF has a concentration of 150 millimoles per liter. Whereas sodium in the ICF, right, should be lower, right? It should be 15 millimoles per liter. And on the extracellular fluid, it has 150. Okay, so exactly what we said. We said that sodium is higher outside than inside, and potassium would be higher inside than outside. Okay, great. That's just kind of rewording everything we said. But if I were to figure out these guys' equilibrium potential, which, by the way, is the point at which these ion movements stop. Okay, so for example, potassium. Okay, it likes to go down its concentration gradient outside. But there's a point where the electrical gradient of potassium starts to catch up to that dominant concentration gradient. And when those two become equal, we will reach dynamic equilibrium and potassium will no longer move. Okay? So imagine this. At start, we start out with a lot of potassium outside and a lot of potassium inside and less potassium outside. We keep going and going and going and going until what happens? The concentration of potassium outside will start to kind of equalize with this concentration inside. And at the same time, we're removing a lot of positive charges from inside of the cell and pushing them out and making the outside more positive. So the electrical gradient will start to kind of catch up as well. The point at which the electrical gradient that is pushing potassium inside, and the concentration gradient that's pushing potassium outside, at the point where they equalize, that's called the equilibrium potential of the ion. Okay? Equilibrium potential of ion. So one more time, the equilibrium potential of the ion is the point at which the concentration gradient pushing potassium out is equal to the electrical gradient pushing potassium back in. For sodium, it's the same thing. It's the point at which the concentration gradient and the electrical gradient equal out to one another. Okay? So where does this occur? At what kind of membrane potential does this occur? Right? Because the movement of these ions will dictate membrane potential. So if we were to just look at potassium alone, right? If we just let potassium reach its equilibrium, it would bring the membrane to around negative 90 millivolts. If we allowed sodium to just move on its own, okay, without like any other ions interrupting it, it would bring the membrane to positive 65 millivolts. Okay? So sodium reaches equilibrium at positive 65, potassium reaches equilibrium at negative 90. All right? Where do we get these numbers? How do we actually calculate these numbers? We calculated them using something called the Nernst equation. Okay? This Nernst equation is a mathematical way of just estimating the equilibrium potential. And, it can be used by this equation. So E is the estimate of the equilibrium potential for our ion of interest. This 61 is a constant. Logarithm is a mathematical operation. CO is the concentration of the ion outside of the cell. Ci is the concentration of the ion inside of the cell. And technically, there should be a divided by Z here, where Z describes the valence state of the ion. But it doesn't matter. If you plug in those concentrations that I mentioned to you, okay, these ones right here, you will get a number close to negative 90 millivolts. All right? Now, take a note here that to actually measure these values, like without having to estimate them using an equation, we would have to stick something called a microvoltmeter into either the ECF and the ICF, and then measure them. Okay? So that's what we would have to do. Okay, great. So now we know how we actually got these equilibrium potential numbers, and what they actually kind of represent. They represent the point at which the ion reaches a steady equilibrium, all right, where the rate of ion movement outside is the same to the rate of ion movement inside, so it looks like there's no movement, there's no net movement. However, movement is still occurring, but to the naked eye, it looks like nothing's happening because they're moving in and out at the same rate. Now, here's the other thing that's really, really important. If this is truly negative 90 and this is truly positive 65, why is it that the resting membrane potential is negative 70? Why isn't it like somewhere in the middle of these guys? And why is it much more closer to potassium's equilibrium potential? Okay, I will answer this very, 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 very easily. Okay, which is this question right here. Why is it that the cell is negative at rest? Like, why is it closer to the potassium equilibrium potential than it is to sodium? Such an easy question to answer. It has to do with membrane permeability to these ions. Potassium at rest is so much more permeable. Okay, the membrane is so much more permeable to potassium at rest than it is to sodium. In fact, and these numbers are estimates, obviously, but it's been said that the membrane is 50 to 75 times more permeable to potassium than it is to sodium. Okay, but what does permeability really mean? Permeability in this scenario really is talking about the fact that potassium, okay, has more channels on the membrane, okay, compared to sodium. Okay? Well, what kind of channels am I talking about? These channels right here. I didn't draw 3 channels and 2 channels here by accident. There are more of these potassium channels than there are these sodium channels. But what are these channels called? These channels are called leaky channels. Leaky or passive channels. They're always open. Okay? They're a form of facilitated diffusion, right? They're always open, guys. Leaky and passive channels. Great. How much do these guys contribute to the resting membrane potential? They contribute about 80% to the resting membrane potential we know of. Okay? Why is it that you might say that? Well, look at it like this. More potassium channels, which means more potassium will actually move out, okay, of the cell, just passively, right? It'll just keep leaking out of the cell, and it'll keep bringing us to that negative 90 millivolts, right? But potassium's not acting alone here. Sodium exists. Sodium will also be moving in, but in smaller amounts because there are less sodium leaky channels. So instead of reaching negative 90, sodium will counteract some of that, and it'll bring us to negative 70. Okay, it'll make the inside a little bit more positive than it was supposed to be if only potassium was present. Okay? So that's why we land at negative 70 millivolts, okay? Now, you can actually go ahead and calculate this membrane potential for yourself. It can be calculated using the Goldman-Hodgkin-Katz equation, but we're not going to do that today. But really, guys, the most important thing to understand is, pay really close attention to this. The greater the permeability of the plasma membrane for a given ion, the greater the tendency for that ion to drive the membrane potential towards that ion's equilibrium potential, which is what we've been saying all the time. That because potassium is so much more permeable, it drives the resting membrane potential closer to its own equilibrium potential. But because sodium also kind of leaks in, right, and it's a positive charge, it'll counterbalance that a little bit and bring us to this kind of midway point, if you will, between the two equilibrium potentials. Okay? Great. So that is how we generate the resting membrane potential, right? 20% contribution from the sodium-potassium ATPase, right? Because every time it makes the cell just a little bit more negative, okay? But also the main thing that it does is that it establishes a concentration gradient so that these leaky channels can use it to bring the cell to resting membrane potential. At resting membrane potential, there is a steady state that exists, okay? Where the net amount of positive charges that come in equals the net amount of positive charges that go out, all right? So you might be thinking, hey, well, if all this positive charge from the sodium leaky channel keeps coming in, well, wouldn't it just bring the membrane back up, right? No, it wouldn't, because any of that sodium that comes in will get removed immediately by that sodium-potassium ATPase, and we will bring potassium in, which will then go back out, okay? And then that potassium that went back out will then come back in using this. It's just a constant cycle that keeps occurring, which maintains the resting membrane potential at a very steady state, okay? Now, you might be asking me, hey, what about other ions? Okay? And other things that might contribute to this resting membrane potential. Well, other things that might contribute would be these, for example. This large A represents large intracellular proteins, okay? And these proteins are negatively charged usually, okay? Because, proteins, some of them can be very negatively charged. They exist inside of the cell, but they're so large and they're so negatively charged that they just can't cross the plasma membrane. So watch, this guy's going to try and cross the plasma membrane, boom, but he can't. So whenever these potassium charges, right, these potassium ions, they leave the cell, right, not only do they make the cell more negative, right, by kind of, less positive charges being there, but they also kind of concentrate the negative charges as well, like in the form of these large proteins, okay? So beforehand, the presence of these large proteins that are negatively charged would have been counterbalanced by the amount of potassium ions that are inside of the cell. But when potassium ions leave the cell, they leave behind these kind of negative charges, concentrating the cell in them, okay? And thus, cell becomes more and more negative, okay? So these large proteins also kind of contribute to the membrane potential by way of kind of potassium leaving and concentrating them, okay? And, we can also talk about their kind of distribution in the ICF and the ECF, and this should be very easy. In the ICF, they're very large, 65 millimoles per liter, and in the ECF, there's 0 of them because they cannot leave the actual cell. There are other neurons that are involved. For example, we talked about it in the module when we were talking about the blood. We mentioned that one of the principal ions of the extracellular fluid is chloride, okay? And chloride is a negative ion. So there's a lot of chloride just chilling out here, okay? Does chloride contribute to the resting membrane potential? No. In fact, many other ions, such as calcium, magnesium, right, and chloride, they do not contribute to the resting electrical membrane potential in almost all cells. Almost all cells, okay? Even though they play other important roles in the body, they just don't contribute to the membrane potential in, again, most cells. And the reason for chloride in this case is because the equilibrium potential of chloride is -70. -70 millivolts. Hey, doesn't that sound familiar? This sounds familiar. -70. The inside of the cell is -70. So there will be no net movement of chloride in or out of the cell, aka it will have no effect on our membrane potential. Okay? Even though that chloride in the ICF is around 7 millimoles per liter, whereas in the extracellular fluid, right, again, it's the principal anion of the extracellular fluid, so it should be pretty high here, and it is 100 millimoles per liter, right? Even though the concentration gradient exists for chloride to move into the cell, its electrical gradient, right, is matching that concentration gradient, which means that the ion is at equilibrium, all right? Meaning that there's going to be no net movement, which means no net difference in charge, which means no contribution to the membrane potential, because the membrane potential is a difference in concentration of cations and anions, right? Which are just charges. Okay, so things like chlorides don't actually have a effect. All right, and you know, I can write it here for you, that meaning no net movement of chloride in or out of the cell at resting membrane potential of -70. Okay? Now, if there are certain cells that have a resting membrane potential that is lower or higher than this, then things are going to be different, and we'll talk about that in upcoming videos. Okay, but in most cases, these kind of chloride just does not contribute to the resting membrane potential, and the principal ions that do are going to be potassium and sodium, based on what we were talking about, right? Based on the ion permeability and all that stuff. Okay. All right, and some final clarifications I do want to make is that these leaky and passive channels are very specific to their specific ion. So this is a leaky potassium channel, and it only lets potassium through. This is a leaky sodium channel, and it only lets sodium through. Okay? Also, I want you to remember that the sodium-potassium ATPase uses ATP. Okay? A lot of people kind of confuse this concept of an ion reaching an equilibrium with the cell being at a steady state in -70, because they think, okay, in both scenarios, there is no net movement of charges, right? Which is true. However, in this steady state where resting membrane potential exists, we have to use energy, ATP, right, to keep this kind of process going. In an equilibrium scenario where an ion reaches equilibrium, there is no energy involved. It just kind of counterbalances, right? The electrical gradient counterbalances the concentration gradient, right? They match together, and thus the ion just kind of stops having a net movement. Okay? That's an important distinction to make, I think. Now, that is going to finish everything off with this video, okay? Guys, if you really enjoyed the video, if you liked it, if you truly learned something from it, feel free to like, subscribe. I would really appreciate it. And if you have any questions, leave a comment and I'll answer. I'll see you in the next video when we talk about how we can actually change this membrane potential by initiating something called a graded potential. Okay? See you there.